Now, maybe you're noticing that these K values are so small and that we are not getting many ions in our solution at all. And you might even remember our solubility rules from the beginning of the year. And you might even be thinking, hey, some of these things were on our insoluble list. So we need to talk about that a little bit. So, salts that we classified at the beginning of the year as insoluble, they will dissolve a tiny, tiny, tiny bit in equilibrium. And the amount that they dissolve is going to directly relate to the value of their K. Now, we will call this Ksp for the solubility product constant. So everything is still the same. It's products over reactants. We don't put solids in the equation. We're just putting an SP for solubility product constant. Now we will be using Appendix D in the back of our book to get values of KSP for various salts. And again, the smaller the KSP, the less soluble that particular salt is. Now, as we were already seeing in our previous example problem, is you can use your K expression to figure out the X value and then the amount of ions that are dissolving and the amount of salt that did dissolve. And then from there, you could even figure out the grams of the salt that had dissolved too. All right, so we have two examples. In our first example, we have silver chromate being added to pure water at 25 degrees Celsius. Some of the solid remains undissolved, so that tells us the maximum amount has dissolved. We've made a saturated solution. The silver concentration in the saturated solution is 1.3 times 10 to the negative fourth. And we are looking for the value of K. So here is our reaction showing the silver chromate dissolving, and the K expression is already written out for us. So if it's helpful, we could do an ice chart here. So we're going to start with none of my ions because this is not a common ion. We will be gaining 2x of the silver and x of the chromate. So that's what we will have at equilibrium for those two. So we can plug that into my KSP expression. So the silver is going to be 2x squared, and the chromate is going to be just x. Now, up in the problem, they told us that the silver concentration is 1.3 times 10 to the negative fourth. So if I know that's the value of 2x, then I know that my chromate would be half of that. So if 2x is equal to 1.3 times 10 to the negative fourth, then I know that x would have a value of 6.5 times 10 to the negative fifth. So that is what we will then be putting in our K expression. All right. And once we put that all into our calculator, then we get our KSP having a value of 1.1 times 10 to the negative 12th. So again, we just use our ice charts to figure out that the silver concentration would be 2x, the chromate would be x based upon the information that we were given in the problem. We knew the value of 2x and the value of x, so then we just plugged it in and get 1.1 times 10 to the negative 12. That is a very small KSP. So that tells us that this salt is not very soluble. Only a tiny, tiny bit will be dissolving. So in lab, we would not even be able to see the small amount that would be dissolving. It would appear like it was insoluble. All right, in our second example, we have calcium fluoride that has a small Ksp value. So, again, telling us that it is not readily soluble. The small amount of the solid that will dissolve would turn into the calcium ion, and then two of the fluoride ions. We do not have common ion present, so we would be starting with none of the calcium, none of the fluoride. We would be gaining 1x of calcium and 2x of fluoride. So at equilibrium, it would be x and 2x. We don't even bother filling in the calcium fluoride since that's a solid and that would not be present in the equilibrium expression. Speaking of the equilibrium expression, we would write our Ksp is equal to the concentration of the calcium ion times the concentration of the fluoride ion squared, because there are two of them. The value for our Ksp is 3.9 times 10 to the negative 11th. So then we plug in x for calcium, 2x squared for the fluoride, which would give us 4x cubed. So then we divide the 3.9 times 10 to the 11th. We will divide that by 4. That would give us x cubed. And then we will take the cube root of that. And our value for x is 2.13, or 2.1, because we only want two significant figures, times 10 to the negative 4th. So that would be the amount of the calcium ion that would be dissolving. If we were looking for the fluoride, we would double that. But what we were actually asked to find was the solubility of the calcium fluoride in grams per liter. So I know I didn't fill in my initial amount of calcium fluoride, but it still would be the amount that would be dissolving would be 1x because it has a coefficient of 1. So this is telling me the molarity of what is dissolving. Now we know that molarity is equal to moles per liter. So we'll write that in. So we'll erase that capital M and do moles per liter. If I want to get this to grams per liter, all I have to do is to get rid of moles and find grams. So then I would do 1 mole equals the gram formula mass of calcium fluoride. And if I add up calcium and 2 fluorines off the periodic table, that would be 78.1. And so then I would be able to calculate that, and I get 0.017 grams per liter. So that tells me out of a liter of water, I am only dissolving 0.017 grams. So again, that's why in lab it would make it look like this is not soluble, because only a tiny bit is dissolving.